Thank you for being here tonight and welcome to WestFest 2022. Before anything else, we would like to acknowledge the land that the Ohio State University occupies is the ancestral and contemporary territory of the Shawnee, the Potawatomi, Delaware, Miami, Peoria, Seneca, Wyandot, Ojibwe, and Cherokee peoples. Specifically, the university resides on land ceded in the 1795 Treaty of Greeneville and the forced removal of tribes through the Indian Removal Act of 1830. We want to honor the resiliency of these tribal nations and recognize the historical context that has and continues to affect indigenous peoples of these lands. WestFest is the Ohio State University's annual Science and Sustainability Festival. This program is made possible through a grant from the Ohio State Energy Partners. I'm Monica, and I'll be behind the scenes making sure everything goes smoothly. If you share about WestFest on social media, please use the hashtag OSUWestFest. We have a few short announcements to share before the program starts to ensure that all attendees have the best experience possible. And you have the ability to enable or disable the caption, seeing the caption to suit your needs. We hope to make the webinar as interactive as possible, and we definitely want to hear from you. Please feel free to add your comments in the chat and post questions for the presenters in the Q&A. We will be taking both periodically throughout today's program. If you receive one of WestFest's activity kits, you have everything you need to follow along with us at home. Make sure you have the activity bag labeled Be the Glacier. Don't worry if you don't have an activity kit. You can still follow along with today's program. A digital activity booklet with supply lists and instructions for all our virtual programs is available on our website, go.osu.edu/westfest. You are attending Build the Glaciers, presented by Dr. Tom Chudley, Jason Cervenec, and Kara Lamencia from Byrd Polar and Climate Research Center. I am going to turn it over to Kara now to get the program started. So Kara, take it away.
Okay, thanks, Monica. So my name is Kara. I am a PhD student. I work at the Byrd Polar and Climate Research Center. I'm in the Ice Core Paleoclimatology group, which means that we drill into glaciers and ice sheets and we extract gases to reconstruct our Earth's past atmosphere. And there's a bunch of other people that work at Byrd, and so I'll let Tom and Jason introduce themselves real quick, and then I'll show you a video and then we'll get going. Jason?
So my name is Jason Cervenec. I'll be helping everybody make their flubber or their glacier today. And I lead the education outreach team here at the Byrd Center.
Hi, I'm Tom, and I'm a scientist at the Byrd Institute in the Glacier Dynamics Research Group.
Great. So Byrd Polar is comprised of a bunch of different research groups. There are people that work in both the Arctic and Antarctic regions, and people that do work on other types of ice and snow around the world, and all kinds of other climate and geology related work. But instead of me rambling, I will show you our video that gives you a little bit better of an explanation and a quick overview of what we do. I will stop screen sharing. And if you want to go ahead and get out your supplies, if you have them from the WestFest kit, or you can assemble your own, Jason will walk you through how to build a glacier.
Okay, so if you have your box and you've opened everything out and spread it out, wonderful. If you haven't, now is your time to at least go to the pantry or wherever you keep your school supplies and grab your Elmer's glue. You might have some leftover from, if you have an elementary school or in the house, from last year. Borax detergent, which these are obviously much larger containers than you have in your kit. These are the size we buy at the Byrd Center because we make a lot of this glacier flubber. The container you have will be exactly, of glue is exactly the right amount you'll need to mix up your flubber. And the bag you have of borax is the same size, but today I'll be measuring everything out in case you want to do it at home by getting your own materials. You also are going to need some warm water, and that's just warm enough that it comes from the tap, some cooler water, and some measuring cups and measuring spoons, and a few bowls and plastic containers to mix everything in. So before we start, if you're still getting your stuff out, I'd like to have everybody open up their chat, and I'd like you to drop in an answer to a question. But I don't want you to hit enter until I do a countdown. So we're going to give everybody about 30 seconds to type their answer to this question. And I'd like you to answer the question, what is a glacier? So if you're with somebody, talk that over and type in what you think a glacier is, what features it has to have to be a glacier. Type it in, but don't hit enter until I count down. Okay, well, what makes a glacier is, one, it has to be made up of ice, and two, it is pulled downhill by gravity. And if you think about it, we have something else that's made of water that is also pulled downhill by gravity, and those are rivers. And so a lot of times we consider a glacier simply a river of ice. It's made up of of this big mass of ice. It flows downhill, and it doesn't just exist 1 year, it exists year after year after year. And that's what makes a glacier a glacier. So we're going to make an example of something that flows just like glaciers. So the first thing you want to do is you want to go ahead and measure out your glue. So if you happen to have the glue that we shipped in the packet, you don't have to measure this out. You can just empty the entire bottle of glue into the Ziploc baggie. Obviously, I have much too big of a container, so I'm going to measure out this 1 cup or 1/2 cup of glue. And we're going to put this in a Ziploc baggie. The reason for the Ziploc baggie is you're going to mix it up. You could use a bowl and something like a spoon or a wooden spoon. To be honest, I find it pretty easy with the bag because it's easier to kind of knead it like bread dough. And it is pretty messy at first until it starts to clump up, coagulate. You got a spatula in the kitchen and you're there. This is a really good point to use that. If you are doing this in a place that's not in your kitchen, I do recommend putting newspaper, drop cloth out or something like that. If this mixture dries up on your carpet, it tends to be a little hard to get out. So I would try not to get it on the upholstery in your sofa. So we have that, we've added that. Now the next thing you want to do is you want to go ahead and take some warm water. So I just have a thermos here to keep this warm. And we're going to measure out 6 tablespoons. So those are the larger spoons in your kitchen. I'm using a measuring spoon, but you could use the ones you have in the drawer for serving food. And I'm going to measure 6 teaspoons of this, and I'm going to drop it in there, and then we're going to mix it up really well. So if you happen to be ahead and you've already measured these 6 out, you can start the process of sealing the bag, burping all the air out, and then we're going to go ahead and kind of knead the glue to get this water mixed in. Once again, burp the air out a little bit, otherwise this is going to explode and you're going to have glue all over the place. And we just want to go ahead and mix this in really well till the water is mixed with the glue. Since it's warm water, it's going to mix pretty quick. And this is going to make the glue really, really runny. So the thing we're making is called flubber. It flows very slowly like glaciers. And when we mix this up, it's going to make something that's not quite a solid and not quite a liquid. And it's called a non-Newtonian solid, which means it's solid, but it flows like a liquid. So it has some properties of both. Okay, so that's our glue mixture. So we're going to let that sit there for a second. Second thing you want to do is you want to mix up the borax and a different amount of water. So for the borax, we need 1.5 teaspoons. I'm just going to use this container I have sitting around. So teaspoons are the small spoons you have in your kitchen. So we're going to take 1.5 of those. If you have the baggie that shipped with your WestFest kit, you're going to use the entire amount that's already pre-measured for you. Save you a little bit of time. Borax is used as laundry detergent. It's kind of an old school laundry detergent. So you can find it in most grocery stores. It's only about $3 or $4 for this entire container. So it's not very expensive. And then I want to go ahead and mix this up with about 1/3 of a cup of cool water. Once again, it doesn't have to be ice water, just cool. Measure that out. And then we're going to do some mixing. So grab a spoon. You can just use the measuring spoon. And we're going to mix this up as well as we can. Want to try to get most of the solid material of the borax to dissolve. There's a little bit if it's not, that's okay. But it will take a second or two to dissolve. Now, you do have the option at this point, as we're mixing this up, to put some food coloring in here. I'm not going to do that tonight, but if you have food coloring in your kitchen, this is the best time to mix that food coloring in, and you can make some of the flubber that's a different color. If you want the most authentic color, maybe a light blue would be in order. Food coloring can stain stuff though, so once again, if you're doing this on the carpet in your living room, it might not be a good idea to include that. Sometimes when we make 2 sets of flubber and want to show how the glaciers flow side by side, we'll use 2 different colors. Still mixing up. Almost there. So we're going to do in a second is I'm going to open up this bag. If you have somebody who's helping you, that'd be a good thing for them to do. They can hold it open. And you're going to pour all this liquid in there. And then we're going to mix it up and kind of knead it again. And then we should have a pretty dramatic transformation that'll happen here in a few minutes. So go ahead and burp the extra air out so it doesn't explode on you. Make sure it's sealed real well. And we're going to just mix this up for about 2 more minutes. And then we'll open it up and we'll see what transformation has happened. If you have any questions as we're doing this, feel free to drop it in the chat and Monica can relay those to us. We did send you some maps with the materials. We're going to pull those out. We're going to use them in a second. One of them's in your WestFest activity book that had the instructions for making this. And that's a map of North America shown right here. And the second one is there's a really nice book, a geofact sheet that comes from a Division of Natural Resources in the state of Ohio. And we're going to use this at the end, but it shows you what some of the glaciers look like in Ohio and some of the areas that they covered. And from that, I kind of have a zoom in of a map that I'm going to use here in a second. It's kind of cool because when we asked the Division of Natural Resources for these sheets, we looked in the back for some of the information they used to write the article. And our center was founded 63 years ago. And the person who did a lot of the research that made that up was actually our director, our first director of the Byrd Center, which was neat to see his name listed there. Okay, so this is working pretty well. We're almost there. There might be a little bit of extra liquid at first. We're just trying to mix it to make sure all this is blended in really well. If there's any extra, we can always pour that off. I will tell you, if you make this stuff this time of year in the winter, kind of fall versus in the summer, the texture tends to be a little different, so don't be surprised by that. If it's warmer out, the flubber tends to be a little bit runnier. If it's really cool and dry, it tends to be a little bit thicker. Like those of you that were tuning in, if anybody tuned in this morning, you're going to see the water I used this evening is a little bit warmer, and the flubber is definitely a little bit runnier than it was this morning. Okay, we're getting there. So you can go ahead and open it up now. You'll see as I'm starting to mix this, this is a little bit different than that glue we were using earlier. The glue would just be runny, and you can see this is already starting to get stretchy and have some coagulation to it. Once again, we're going to keep mixing here a little bit more. For those of you that are interested in chemistry, the process that happens here is pretty cool. Proteins and a lot of our foods change when you heat them up or if you add detergents or salt. So if you think about putting an egg on the skillet, it's really runny and it's transparent or semi-transparent. You cook it, it changes to more of a solid and the texture changes in the color. The same thing happens here. Glue has a lot of proteins in it, and by adding this detergent, all those proteins that are kind of running and sliding past each other are getting stuck and clumped together, and it's making this solid that is not running like glue anymore. So actually my flubber is almost there. I got a little bit of extra liquid in the bottom, which is not a bad thing. But I'm going to actually take this out of here now. And I'm going to put it on my map. Now, keep in mind, you do have a computer next to you, so I would not try to use the computer right after using your flubber. But I would like to ask you something. On your map you have, you can see this is a map of North America. And we mentioned glaciers. Tom's going to talk in a few minutes about something even bigger, massive things that are even bigger than glaciers. And on Earth, there's currently two places we find these things called ice sheets. One is Greenland and one is Antarctica, but there used to be a third one. And that third one was centered right over here, which is Hudson Bay. There was supposed to be a star there in your instructions, but somehow that star migrated down to Chicago. It's actually supposed to be up here in Hudson Bay. So this ice sheet used to be centered over Hudson Bay. So I'd like you, once you get your flubber, to go ahead and drop that right into Hudson Bay. And we're going to kind of watch and see what the flubber does for a few minutes here as it slides across North America. So this ice sheet that was located there was about a mile tall, actually more than a mile tall in its center. When it got to Ohio, places like Toledo or Cincinnati, it was about a mile tall, and in Columbus, it would have been about a half mile thick. So if you were back in the day and you were on the ground, you'd actually be crushed by a half mile of ice. And if you're standing on the top of the ice, you'd have a half mile of ice between you and the bedrock. So what I'd like you to do is, if you're following along, take a second and tell me, if you were in Ohio, which direction did the ice sheet come into Ohio from? Did it come from the north? Did it come from the south? Did it come from the east? Or did it come from the west? And we'll see if anybody wants to post an answer to that. Feel free, as soon as you type it in, to go ahead and hit enter, and let's see what we've got. Okay, so Alyssa says north. You're getting a clue if you're watching the flubber on my table right now. You're starting to see the flubber actually come into central Ohio where that yellow dot is. Anyone else? Okay, so it is indeed from the north. So this mass of ice actually pushed into Ohio. It brought a lot of changes with it. So if you're in Ohio, we have a lot of fertile farmland. A lot of those soils, the material that makes them up, got swooped up in Canada and pushed into Ohio and deposited here, especially when the ice retreated. We also got the giant glacial erratic. So if you go to a lot of the metro parks or the city parks in Ohio, you might see large boulders in the forest or in the farm fields. They've maybe been moved to the side by the farmer who didn't want it there. There maybe is a plaque on it for something. A lot of those rocks come from bedrock that's not in Ohio. They actually brought in from Canada. The glaciers brought them in and deposited them here. And at the end, we'll talk about the glacial grooves in Kelly's Island. And if you go up there, it's kind of cool. And you look at the orientation of the grooves actually orient themselves from north to south, or roughly from north to south, because they were scraped by the glacier as it moved through the state. Even the Great Lakes were a feature that was formed by the advance of these ice sheets. Now, one more thing before we pass this on to Tom. So I'm going to put out my map of Ohio. On that geofact sheet, there is a diagram showing Ohio, but I can also put my ice sheet right on the state of Ohio, and we can watch how it advanced across the state. It's kind of located up here in the north. You can see it advance. One of the things that's pretty interesting about this, the way the glacier advanced, is it moved through the state and it actually formed different lobes. And some of the features, when you go ahead, if you want to put this down, you can put your finger in the way, and we can see why some of those lobes formed. One of there was a high point actually in Bell Fountain where you have one of the ski slopes, and as the glacier advanced towards that point, it couldn't easily go over the high point, and so it actually kind of spread out and went around that high point that makes up Mad River Mountain, and there's two lobes that formed. And if you look at the soils in the state, you can see these little swoops that are here, the two different lobes, as they went around that high point feature. So you can see this advancing from the north to the south, but we have a lot of evidence in the soils that are left and the mounds of debris that were left as far as the glaciers traveled that tell us how far they advanced. So on this map, you see greens and browns. The browns are one of the glacial advances, and the one that happened after that was the greens, and those glaciers didn't advance as far, so they didn't cover up that first series of glaciers. And when they retreated in different periods, and they left these moraines or these debris piles in front of them, which makes up some of the hills you might drive through. If you go through north and west Ohio, there'll be some rolling hills in places, and that's as far as those glaciers traveled. So with that, I'll ask if there's any questions before I kind of pass the torch here to Tom, and he's going to talk a little about some of the work, not just on the ice sheets that are from the past, this Laurentide ice sheet that affected Ohio 11,000 years ago, but the two ice sheets we have on Earth, the one in Greenland and the one in Antarctica. Okay, Tom, I think it's all yours.
Okay, great. Thanks a lot. So as I mentioned earlier, my name is Tom and I'm a glaciologist here at the Byrd Institute. Glaciologists are scientists who aim to understand the processes and changes occurring in ice around the world. And my job involves using data from field and from the field and from satellites to understand how the global ice sheets are changing. So let's just recap on what ice sheets are. Ice sheets work in exactly the same way as mountain glaciers that you might have seen or visited and that we've been building today, but they are bigger. Officially, they're defined as anything bigger than 50,000 square kilometers, but I prefer the informal definition is that you know one when you see one because they are continental on scale. We can see here there are two ice sheets in the world today. There have been many in the past, including the Laurentide in America and Fennoscandian in Europe. But we currently have two. That's Greenland here on the left and Antarctica on the right. They contain so much ice that if all the ice in Greenland was to disappear, sea levels would rise by over 7 meters. That's about 23 feet. And in Antarctica, that's more like 58 meters or 200 feet. So on the next slide, we can get some pictures for scale. This is a picture of me in the bottom right, standing on some ice, looking quite small in comparison. But this isn't an ice sheet. If we zoom out, we can see it's actually a glacier called Solheimajökull in southern Iceland. So we can just zoom out one. Yeah. And you can still see tourists there a bit just in the far right of the screen on the other side of the lake. If we zoom out further and we look at a satellite image, we can get a sense of how big this is. The lake now is this tiny thing in the bottom left, and we can see this river of ice that we talked about, this big flowing river of ice coming from the top right. If we zoom out again, we can see that Solheimajökull, the glacier, is actually coming from an even bigger mass of ice called Mýrdalsjökull, which is an ice cap. So a glacier that's got so big, it's burst out of the valley that's containing it and is now a big dome existing on the landscape. Zooming out again, we can see that Mýrdalsjökull isn't even the largest ice cap in Iceland. And if we zoom out again, we can see that even Iceland itself is dwarfed by Greenland, which is about the size of Mexico and averages about a mile thick. So the ice there is about twice as tall as the Burj Khalifa, the world's tallest building. And this is Antarctica, which is similar in scale to the continental USA. So the next slide again, we can see that like most glaciers on Earth, as the world warms up, ice sheets are seeing melt. This is drone footage over Greenland showing melt from the ice sheet making its way to the margins, where it then enters into the sea and contributes to sea level rise. The melt is about 1 billion cubic meters a day. So that's a cube of water, 1 kilometer by 1 kilometer by 1 kilometer on a side, or about 400,000 Olympic-sized swimming pools per day entering the ocean. But on the next slide, we can remind ourselves that from what we've talked about today, what makes a glacier special isn't just that they melt like an ice cube, but that they flow like a river. In Greenland, snow and ice accumulate in the center of the ice sheet and then work their way out towards the margins over the course of hundreds or thousands of years, where they concentrate in what we call outlet glaciers. These are fast-flowing rivers of ice where the ice can move out to 50 meters a day, so about 160 feet in a single day. And this is ice that can be hundreds of meters thick at the front. On the next slide, again, we can see an example of what an outlet glacier looks like in the field. This is Stor Glacier in West Greenland, which I visited multiple times in the past on fieldwork. Stor Glacier is Danish for big glacier. So this is quite a large example. It's about 3 miles across and moves about 20 meters a day into the ocean. The glacier is moving from the left, and on the right is the ocean, which is covered in the chunks of ice and sea ice, and what we call a melange or a sikusak. When ice falls off the ice sheet into the ocean, we call this calving. And so this next image hopefully will show us an example of a calving event. Yeah, there we go. This produces icebergs, and some of these icebergs can be enormous, hundreds of meters in scale. I think we're all familiar with the iceberg that sunk the Titanic, and that iceberg originated in one of these calving events, likely from a glacier just south of this one. This calving is so significant that, in fact, only about half of all sea level rise from Greenland is caused by melt from the surface. The other half is caused from this ice directly calving into the ocean, and we call this discharge. So between these two processes, melt and discharge, we've seen sea levels rise by about 20 centimeters since the pre-industrial period. And realistically, we're on track to see sea levels rise by about 1 meter or 3 feet by the end of the 21st century. This map of the southeastern United States visualizes what this might mean. The dark red shows the regions of the coast that are at risk from 1 meter of sea level rise in this context, and we can see places like New Orleans and Miami and Jacksonville are all beneath the level at which seas are going to rise in the next 80 years. So people being born today will live to see this world and face its challenges. So going on to that, we can sort of understand why ice sheets are important, but now we need to understand how we learn about them. So on the next slide, we can see an example of 2 satellite images from the European Space Agency Sentinel-2 optical satellite from the 11th of July and 3rd of August 2017. And this is again of Stor Glacier in West Greenland. And if you look in the bottom left of the image, particularly where you see these fractures and marks in the ice, hopefully you might be able to see them move between these 2 images. If you can't, that's okay, because when Jason clicks the slide, we'll be able to see that a computer can see these images. So we use a technique called feature tracking, where a computer can identify groups of pixels flowing through the image, and we can reconstruct how a glacier moves and flows. And here you can see going towards red, where red is faster, we can see this river of ice working its way towards the oceans. On the next slide, we can see the other end of the spectrum, which is what I call in situ geophysical instrumentation or fieldwork. On the left is a setup we have made on the ice sheet. Largely, it's a big car battery and some solar panels and some wind generators, but there's key scientific equipment too. On above Sam there in the orange jacket, you can see this white UFO-shaped thing, which is a dual frequency GPS that's measuring how fast the ice is moving to the nearest centimeter over the course of hours. On the left, again, you can also see things for measuring wind direction and snowfall, etc. On the right is a borehole that was created by pumping hot water down to the bed of the ice sheet. The ice is about 1,000 meters thick here. And my colleague Charlie, she is implementing a very long string of cable with seismometers and packages to measure temperature and pressure and tilt, so we can listen to the ice sheet and measure its temperature. And also to give you an idea of the melt rate here when we're on field work, the poles have to be about 6 meters long when we put them in the ice, because when you come back the next year, this is what's happened to them. There's been about 2 or 3 meters of ice melt occur in the intervening 12 months. So you've got these 2 methods that are either very precise methods of a single location that's very intensive. And on the other end of the spectrum, if we can just click through to the next slide, we can see there are very coarse measurements using satellites that can take place over days or weeks or months, but measure an entire region. It would be nice if we can click the slide to see something in between these 2 scales, something that can measure change on the scale of meters or hundreds of meters over the course of hours. And this is our attempt to do so using an uncrewed aerial vehicle or a drone that we built in-house in our lab. It's made of hobbyist remote control aircraft parts, open source navigation software, duct tape, prayers. And despite my soldering skills, on the next slide, we'll be able to see it fly a pre-programmed flight route of up to 100 kilometers in length, consisting of overlapping flight lines. And I said for scale, the front of this glacier is about 3 miles across. I'm not getting a good view of that video, but hopefully you're getting something better than I am. We trigger the camera at regular intervals to obtain overlapping footage of the glacier. And much like a 3D movie where we reconstruct 3D images by having our 2 eyes set slightly apart, by having these images being taken slightly apart, we can stitch them together into a 3D model of the glacier. So this model is has about a 10 centimeter resolution over an area of approximately 10 square kilometers. I've put these 3D glasses there to remind us how we make these images. And on the next slide, we can see the kind of quality of data we can get from this type of setup. We can see that these velocity fields that I showed how we make earlier can be applied to 2 UAV images that were taken about 8 hours apart. And we can get very detailed knowledge of how this glacier is changing on hourly timescales. So if Jason would just like to click, we can identify a carving event here on the right. That funny little bit where it suddenly becomes very red is the ice beginning to peel away. We identify this in this 8-hour gap. In the next day, that entire block of ice falls away, which is about 1,000 Olympic-sized swimming pools worth of ice. So this is our goal, to obtain these kind of in-between measurements between point data in the field and very large-scale data from satellites. I think that's all I have to say. Thanks.
So we can open up the floor for any questions that anybody wants to ask Tom. or Kara. And I guess maybe the question I'll start out with is one of the ones we had earlier today, which is what is the thing that most interests you or is your favorite thing about glaciers? And we'll start out, Tom, with you.
Yeah. Although I haven't had time to include it in this presentation, I think the most interesting thing for me is the superglacial lake drainage event. So when lakes and ponds form on the top of the ice sheet across Greenland, they can be up to half a mile across and tens of meters deep. But they can disappear in the span of about 4 hours when they fracture the bed of the ice. And we've been in the field and we've watched an entire lake disappear in front of us. And they go down to the bed and continue to do funny things to the ice sheet when they get there.
And so what's that process look like? Where does the water end up going? It just drops all the way through the glacier, or what's...
Pretty much, yeah. So the crack opens and an entire lake goes through in a few hours and then it closes again. But what it can do at the base, it kind of works like a hovercraft. It can lift up the ice sheet and kind of shunt it forward and then push more ice towards the margins like we see here for more carving to occur.
Thanks. And Kara, what about you? You even though both of these individuals are working with glaciers, they're asking very different questions. So Kara, what it fascinates you the most?
Yeah, well, I'm a little different. I'm not necessarily looking for areas of flow. I like when the glaciers aren't moving, but I think the thing that fascinates me the most is how much information they can hold. The record we have from Antarctica is 650,000 years old. And so we're able to look at our past environment from that duration of time, which is really, really neat.
And what are you looking for in the glacier that tells you what was happening that long ago?
We look for everything. We use oxygen isotopes to reconstruct temperature. We look for levels of gases like methane. There are other elements that help us show things like drought, such as chlorine and calcium. There are layers of volcanic ashes from past eruptions we can use to help date back and forth, and other trace metals like black carbon and heavy metals show us things like fires and even atomic bomb testing in the early 60s.
Okay, so even humans get our fingerprint deposited on glaciers.
Yes, and sometimes we even find things like bugs and fragments of shells, and everything gets preserved in the ice. So we have a nice sort of picture to walk us back through time.
Nice. Well, as we kind of invite people to drop any last questions you have there. It could be a question about science. It could be a question about field work. It could be a question about what it's like to work in a laboratory or in Ohio State. One thing I did want to share with everybody is these are our social media feeds and our website. We do have free tours of the Byrd Center every month, and by special arrangement, we also do programs with schools and have rock boxes we send out. If you didn't want to enjoy exploring a glacial landscape, we do have one in Ohio. Well, I do recommend you see that in person. We have a VR tour which is available. So if you go online using this QR code or the link provided here, the glacial grooves on Kelly's Island and some other features of the island are available through VR. You can also use a tablet or a smartphone or a computer to explore. You don't have to have a VR headset. And I know tonight Tom mentioned one of the glaciers in Greenland, Jakobshavn. We do have a tour of that site as well. So all the VR tours we have feature icy landscapes on Earth or places that were dramatically altered by ice in the past. With that, it looks like we don't have a lot of questions. We've had a quiet crowd here tonight, Monica. Maybe everybody's going ahead and eating dinner at the same time. But I think I will pass the torch back to you.
Thank you all for attending. WestFest will continue through Saturday, October 22nd, so there's still time to register for other programs at our event website, go.osU.edu/WestFest. If you have any questions about the event, feel free to email us at westfest@osu.edu. And that concludes today's program. So hope to see you again in one more of our programs, and have a good evening.